Hi everyone, I'm Dejice Jacob. I'm going to be talking about pricing Python parallelism, a dynamic language cost model for heterogeneous platforms. This is joint work done with Jeremy Singer and Phil Trinder at the University of Glasgow. When I talk about heterogeneous architectures, I'm talking mainly about CPU and GPU devices. Now, ACM fits into the broader context of Alpina, which is a framework for automatic loop parallelization. It does hybrid static and dynamic dependence analysis on loop nests, and JIT compiles code for the CPU and the GPU. It augments static analysis with dynamic analysis to parallelize loop nests. Now, ACM fits into this mold, and it's an analytical cost model. It's parameterized on the hardware characteristics of the accelerator that it's trying to JIT compile for. Now, it's dynamic in that if Alpina changes the code based on the dependence analysis that emerges at and the dependence structure that emerges at runtime, the cost model adapts to this. And it's lightweight in that because in a JIT environment you don't want any prediction latency. Let's look at an example here. Two statements that are dominated by a nested for loop, two nested for loops. The dependence analysis is complicated. The static analysis is complicated by the values of the domains not being known, the domains of the loops not being known, and this loop invariant k. So at runtime, if for instance IM and JM turn out to be 32 and 1024 and k is 64, S1 can be executed in parallel. All instances of S1 can be executed in parallel, but on S2, because of the cyclical dependence carried by the outer I loop, the outer I loop should be executed sequentially around S2, allowing the inner loop to be executed in parallel. If, for instance, the same loop can, with the same domain sizes, the k value turns out to be 8, then both S1 and S2 have cyclical dependencies that are carried by the I loop, and the whole graph has cyclical dependencies in it. So the outer I loop has to be executed sequentially around both S1 and S2, while and then the inner loop, the J loop, can be executed in parallel. So how do we model this? Now, ACM is a relative cost model. It doesn't predict the actual total time. It only figures out and compares runtimes between the different costs that come out of for each of these devices. Let's assume a statement S, and if that statement S inside a loop nest has an abstract cost I interpreter. Now, the total cost for that entire statement for every single instance is going to be the product of the domains of every loop that dominate the statement S. And the total cost of the loop nest itself is going to be the sum of all those costs. A similar equation can be made for the CPU. It JIT compiles CPU code with an abstract cost I CPU for each statement instance. Things are a bit more complicated now for the GPU because of the SIMT architecture of the GPU. You have a large number of hardware threads, and it's a hierarchical tiered structure now of threads. The grid is first divided into thread blocks, and these thread blocks are further divided into threads. These threads and thread blocks can be mapped along 1, 2, or 3 axes depending on on the compiler. And how do we model this? Now, for any loop nest, we split the loop nest into two sets, the desequential and deparallel for each statement. Desequential is the set of all loops that have to be executed sequentially, and it's executed in the interpreter to maintain all the dependencies. D parallel is the set of all loops that can be executed in parallel for that statement, and these are executed in the GPU. Now the GPU set, the parallel set is then broken down into two more sets. The set DGPU contains all the loops that can be mapped onto a hardware thread in the GPU, and DGPU complement is the set of all loops that can't be mapped onto a hardware thread, and hence the loops in DGPU complement are executed sequentially within each parallel kernel. Now, how do we model this? First, let's look at this second term here. Now, when you have a number of loops being mapped onto threads, these threads are then broken down into a two-tier structure of thread blocks and threads. Now, the function G will return the number of thread blocks along an axis, along an X, Y, or Z axis, depending upon the computational load that's come up at runtime from the domain sizes of the loops. Now, the function G will return the thread block size along a particular axis. Now the term G will then give us is the product of all the number of thread blocks along each axis, and the term G will give us the total number of threads. Now what's lambda? Lambda is an intuitive feel for lambda would be the number of time steps it takes to finish all the computation that's required within the parallel loop nest. Let's look at these four terms. In these four terms, let's look at these four. Let's look at the last term at the very end. This is the total product of the instances of sequential loops that are executed within each parallel kernel. And the third term is the set of all loops that are mapped onto hardware threads and hardware axes, so that you will have either X, Y, or Z on these. So this is the total computation along the set of for loops that are included in D parallel S. To get a feel for how many time steps it takes, we divide that with the number of execution units that are executing in parallel. So now we have the value W, which is the warp size, and on NVIDIA GPUs that's 32. V is the number of warp schedulers in each streaming multiprocessor, and G is the number of thread blocks. Now each thread block is mapped onto a streaming multiprocessor. Now if we had an infinite number of streaming multiprocessors, these three terms would give us the number of time steps it would take to execute the whole computation, but we don't have an infinite number of streaming multiprocessors. Some NVIDIA GPU, excuse me, some NVIDIA GPUs have 9 and others have 30, some have 64. So we multiply this by this term here, G over U, where U is the number of actual physical streaming multiprocessors in an NVIDIA GPU. This is complicated by the fact that the sequential loops are executing in the interpreter, and the parallel loops are JIT compiled for the GPU. So we need to find the point. Sometimes for smaller GPU workloads, the GPU's kernels are much faster and they execute faster and finish before the interpreter can schedule more work for the GPU to complete. That means that the GPU is starved of more work. So we need to find the point at which the interpreter can keep up with dispatching more work to the GPU. And this point is what we call lambda x. It's the crossover point. And we do this by profiling a very simple statement and then finding the number of threads that it takes to give us this lambda x value, where the GPU is not kept waiting for more work by the interpreter. Beyond this point, the GPU will always have work, and the interpreter is able to dispatch more work before the GPU finishes its previous batch of work. And we take the maximum of either this lambda x value, this crossover value, or which is the overhead of invoking the GPU kernel, or we take the maximum of the total amount of work that's being the number of time steps taken by the GPU. Now we have three terms, each with its own abstract cost in it, which is iint, iCPU, and iGPU. Now how do we bring these together? We profile a simple statement and we then profile it with the JIT compile version, the JIT compile CPU version, and then execute it in the interpreter. And we find the value mu, and which is the speed up of the CPU over the GPU, well, the CPU over the interpreter, sorry. Now, to find a relationship between the interpreter and the GPU instance, execution instance, we use this relationship here, psi, where the cost of executing something for on a JIT compile CPU execution stream and the GPU execution stream on the GPU is inversely proportional to the frequency of the execution and the last level cache size. So and the last level cache size also has a cache sharing factor. Now on a GPU, on Pascal for instance, we have a single streaming multiprocessor having 4 warp schedulers, and each of these 4 warp schedulers share 2 L1 caches between them. And all the streaming multiprocessors within a GPU then share the L2 cache. So sigma gives you the number of the amount of sharing that happens between the streaming multiprocessors and a GPU. On the CPU, we don't have a sigma value or a cache sharing value because it's single threaded, and we assume that the entire last level cache is being used by the computation from a single core. And we use these two terms, mu and psi, to get a relationship between the abstract costs of the interpreter and the GPU. Now, here are the experimental results of the cost model. Now, we see that initially the CPU is predicted to be the performant device, and then as the domain sizes get larger, the GPU is faster. Where we mispredict, the optimal value is 1, where we don't mispredict. When we do mispredict, the spikes in the graph give us the penalty for misprediction. You can see for gem there's 1 value here, and for black skulls at the lower end. And here's another more detailed graph. This shows us the time taken, the absolute time taken for each of these benchmarks. The green line is the GPU, the time taken by the GPU, and the black is the time taken by the JIT compile CPU. It's JIT compiled by number, and it's baselined against a PyPy implementation with vectorization turned on. We compare the ranges across which that the ACM mispredicts. You can see that initially the CPU is much faster, and then as the domain sizes grow larger, the GPU takes over, and you can see these blue shaded regions, which is where the ACM is mispredicting. The red regions, we've compared the performance of ACM against a support vector machine trained with all the data that we had, and this provides us with the red bit where the support vector machine is actually mispredicting. So you can see for the gem and Mandelbrot, the support vector machine is predicting over a large area, whereas the ACM is predicting mispredicting over a much smaller range. It's slightly worse in the case of black squirrels, for instance. Now, we've done this for, I've only showed 4 of these benchmarks, but there are 12 benchmarks in the paper, and that's it. The experiments have been done across 3 different platforms. In conclusion, the ACM is a lightweight analytical cost model to select the faster compute device in a heterogeneous architecture to JIT compile for. It adapts to runtime dependence analysis and code generation. There's minimal install time profiling required. It's a one-time install time profiling. And overall, there's a 13.6% slowdown due to the mispredictions. And for ranges, we are mispredicting across 14.3% of all the ranges in our set of experiments. Here are a set of publications for Alpiner itself and the current publication for the cost model itself. Thank you very much for listening, and I'm happy to take any questions.